There we go. Okay. Here we are on day 91. That's 91 hours of programming. I guess that's what? This is our second week. Third week. We're sort of somewhere in our third week of programming, which is kind of exciting. We accidentally started working on the renderer. I don't know how it happened. It just kind of happened. So here we are in Handmade Hero, working on the renderer. And I was trying to talk about bases, but I completely ran out of time yesterday, so we'll kind of have to do a little bit of a reboot here and talk about bases today so that hopefully we can get through them, have enough time to get through them. If you would like to follow along at home, definitely be sure to download day 90's source code. If you pre-ordered the game on handmadehero.org, we're on day 91, so unzip day 90's source code. That's what we're starting with here, and that way you will line up with me. All right, so bases. I have one thing to mention. I don't know if pseudonyms 73 already mentioned this potentially, but I realized kind of after I sort of was sleepily explaining this stuff that when I was talking about linear independence yesterday, I realized I did have a reason why I could legitimately say that linear independence was good. And it was, I had said minimal up here, but really minimal was just a way of saying linear independence, right? Because what minimal meant in my case was I was saying, I said if we have a 2D coordinate system, that means we have two basis vectors, and I said that was minimal. But that's what linear independence actually sort of means. In a 2D space, you can only have two bases without becoming redundant. Like, you will no longer be linear dependent if you go up to 3. So in some sense, you could say that this was meaningful. So if you do happen to want to learn linear algebra and you learn what this is, really these were sort of the same thing. Minimal is sort of a way of saying linearly independent and spans the space, right? So again, not important really for the discussion, but if you should be doing some linear algebra education on your own time, it's probably worth saying that was sort of, I don't know, kind of walked right by it yesterday when I was talking about it, and I was like, I guess I can't really fit linear independence here, but we sort of actually did. All right, so let's go to our little bases discussion here. Day 91, let's talk about bases. I'm going to work backwards from what I actually want in order to try and give sort of a better explanation. Yesterday I was very sleepy, and I felt like my explanation just wasn't very good. So here we go. All right, so I'm on a screen, right? And we sort of already decided that, we had this is what our screen looked like, but it doesn't really matter necessarily what our screen looked like. We talked about it yesterday, which is that the y-axis goes down and the x-axis goes across, which is to say that if the coordinate that you're using for y is to increase, you will move down the screen, right? And so what I was trying to get across yesterday is really you can think of there as being these basis vectors for screen space, which is that the x vector and the y vector that you would say were your base vectors are essentially 0, 1, and 1, 0 in this case, right? Where 1 pixel, is 1 unit, right? So this is like a pixel, and we keep going out in pixels, right? And the screen itself is as wide as there are pixels on it, and the origin, right, the place where our coordinate system starts, the origin is at that 0, 0 pixel, the upper left corner, right? 0, 0 is always the origin of any coordinate system, I should say. Obviously, the 0 coordinate is always the origin, but where it is, it happens to be the upper left corner, right? And so right here we have our two basis vectors, right? Our basis vector y and our basis vector x, and then we have an origin, which is that point right there. And together we can say that this sort of forms, right, a coordinate system. It's a way that we can say where stuff is. And we can pick any pixel on the screen, right? We could pick any pixel on the screen by saying what the x and y coordinates were. We could even pick things that are off the screen by using negative x or y coordinates or ones that are too large. And we can even pick fractional ones. I could pick the center of this pixel potentially, depending on how I want to define it. Like I could define the origin being at the center of the pixel. I could say that it was up at the corner. I have a number of options for that. But let's say it's in the corner of the actual pixel, that upper left-hand corner pixel. This right here could be 0.5, 0.5. So I could talk about that center of the pixel as well. Similarly, I could define a different coordinate system if I wanted to for my for my pixels, where the origin was actually in a slightly different place, right? If I imagine the pixels that are on the screen, and these are the actual, let's say, LCD pixels that we're talking about here, right? I could make my coordinate system origin be right there, right? I could say that the center of a pixel, essentially, conceptually speaking, was 0, 0. And then like each center of each pixel is at, this is 0, 1, this is 1, 0, and so on, right? And here's that x-axis, that y-axis, right? And I can do all sorts of things. I could also say that I wanted y to go up, right? I could say that that's what the coordinate system looked like. So if I wanted to, I could have a different notion of it where we sort of had something that looked kind of like this, where this is the bottom left corner of the screen, right? I could do that and all that. So there's very many ways I can define coordinate systems, and the only important thing is that we have some notion of those three things. We have to have the origin, we need to know where that is, right? And that's a point, right? That's basically saying where that is somewhere in space. And it's the point 0, 0. Where will, if someone specifies the coordinate 0, 0, where will that be? And then we need the bases, right? We need the x basis and we need the y basis vector, right? And that basically tells us what is going on. That's 1, 0, this is the vector 1, 0, and this is the vector 0, 1. Where do they point, right? And so it's hard to think about this. Sometimes it's a little confusing if you're not used to it, because these are all sort of implicit, right? If I ask you where is the origin, well, it's at 0, 0. That answer is always true. The origin of a coordinate system is always 0, 0. So what does it mean to say we have an origin, right? And the answer is that that origin is always defined in some other space, right? And that space may be actual, it may be physical in the real world. Like in our case, the origin of the screen is the actual origin of the monitor. That's what we're talking about when we say where it is. We're talking about where the actual pixel is, in real world space. That's what we're trying to draw to. But there may be fictional spaces as well. Like the world space of the game is a purely fictional space we have created to contain our fictional world. Where is that origin? Who knows? All we know is that it is the origin of our world, and it has no real definition of where it is, right? It's purely virtual. And so sometimes it can be very confusing to talk about these because that stuff is all very implicit. What's the x basis vector? Well, it's the vector that defines what 1, 0 is, but what direction does it point in? I don't even know how to define it. Again, in the real world, the screen's x basis vector, for purposes of our discussion, is what is the line going across the top of my monitor, right? So the reason that you want to start thinking about these, though, is because that's not always the case. Once we start to get into transforms and doing things, which is what we're trying to do now with our graphics, we will start to describe origins and basis vectors in terms of other origins and basis vectors. Because once you have one of these, you can describe other ones in terms of it and do computations on it, right? So for example, if I was to define a world coordinate system where, okay, we know there's a 0, 0, we know there's a 1, 0 vector, that's the x vector, we know there's a 0, 1 vector, it's a y vector, right? We've got the bases, we've got the origin, right? Once I have one of those and I just say that it means something, like the world space, I'm just purely defining a fictional space. Well, once I define that fictional space in my head and say that's what, I have some notion of what it is just mentally, right? Then anything I choose to define that's inside that space can be given an actual specific meaning numerically in terms of that fictitious space that I've created, essentially, right? Because again, we're creating a fictional world. It doesn't have meaning. It's a fictional world of Handmade Hero. Where is the origin? I don't know, right? It's in Handmade Hero land somewhere. But once I have this, I can start to talk about these things, right? Let's say that's the 0, 1, that's the 0, 1 there, right? So if I want to make another coordinate system, I can make another coordinate system, right? I can make another coordinate system here if I want to. And I can say that this is what it looks like. It has an origin, but that origin can now be described in terms of this other origin, this other x axis, and this other y axis, right? So I can say definitively that if you wanted to get to this new origin, you would go a certain distance along the x-axis from the origin of the world coordinate system. You would then go up, right? So I'd go over. You would then go up the y-axis a certain distance, and you would now be at the origin of this other coordinate system, right? Similarly, once I was there, I could then define points in terms of that new origin. And I can define the axes in terms of the existing axes, right? So what would I do to define, to define these axes here, right? Well, I just have to think about them in terms of these existing axes in the other basis, right? Here's that x-axis, here's that y-axis. Well, what is the definition of my new y-axis? This is my new fancy y-axis I'm defining. Well, same thing. I just measure it in the other coordinate space, right? I just say, well, I know I could define it in terms of this x-axis and this y-axis, and so all I have to do is just create the definition for that. And I don't know what that definition actually is. I guess, we're assuming that we want it to be unit length, so it kind of looks like it's roughly at a 45-degree angle, so it's going to be something like 1 over the length of 1 1, right? It's going to be something like that. So let's actually, I can actually tell you what it probably would be, right? So 1 plus 1 square rooted. Where's the square root thing? Square root. There it is. Ooh, yeah. What just happened? 1.4. Okay. This is. I feel like I did it. There it is. Square root of 2. That's what I wanted. 1.4. So now I just want 1 over that. 0.707. Okay, so that's what that is. You'd think I'd remember that number by now. So let's say 0.7. So this is something like 0.7, right? That would be my new y-axis. So that is like the definition of the y-axis in this other coordinate system, right? Now you may ask yourself, why do I care about this at all? Why are you even bothering to tell me this? Well, this is what we want to do to start supporting rotation, right, and scaling. And I'll explain to you why we care about these when it comes to rotation and scaling. So let's suppose I want to define a shape, right? So I define some axis system that is purely imaginary, like I was saying, right? And I start defining some shape in there. And I define my little shape, it's a triangle, let's say, right? And I know what the coordinates are of this triangle in my imaginary coordinate system because, like I said, I defined it, so I can say whatever it is. Let's say this is 1 unit along that axis, this is 1 unit along here. So I know where each of these things is, and I've now got a definition for this shape, right? I could encode this shape by saying where each of these are. Here's 0.0, here's 0.1, here's 0.2, right? I guess I'll use letters for them. Let's say A, B, C, right? I can define these where they are, I can say what their coordinates are, and now anytime I want, I can sort of say, well, in this imaginary coordinate system, here's where they are, right? Well, if I think about these coordinates as a way of interpreting them, as a way of moving along the coordinate system that I defined here, right? It has an origin, all right? And it has an x and y axis, and I have ax, right, ay, bx, by, cx, cy. These are the coordinates of those points in my system, right? I can always think of that construction that I drew before. I drew that construction before where I'm saying move along x for however big your x coordinate is, move along y by however long your y is. Start at the origin and do those two things. You will get to the point, right? Well, that construction allows us to do any kind of rotation and scaling of this shape that we want to do. Because all we have to do is rotate and scale the bases. And by doing that rotation and scaling, we will then be able to read off how our points go, right? Let's say that we wanted to do a rotation of this, right? So I rotate the bases like so, right? There's a y, there's an x, there's my origin. And now I want to do the exact same stuff, the ax, ay, bx, by. Well, I do the same thing. I go a certain distance along there for ax, I do a certain distance up for ay, and that's my new point, right? Start at the origin, go like this. I do the same thing here. For b, I guess I go this way. There's my b. I go all the way out there, go up. For my c, I go to the middle and go up a long ways, right? And so if I reconstruct those exact motions, right, I produce the shape, You see that? It's the exact same shape, well, modulo my lousy drawing, it's the exact same shape, constructed, rotated. What would happen if I scaled it, right? What would happen if I scaled it? Well, let's say I scaled the y-axis to be really long. So instead of here, where the length of the y-axis was 1, I am going to take the length of the y-axis to be 2, twice as large, right? But the x-axis will stay the same. Well, now, I get exactly the same results along x, right? So my shape looks exactly the same when viewed on that. But when I go to sort of go up the y-axis, I go much longer, and so my shape elongates dramatically, right? See what I'm saying? So by doing that, by changing the bases, we can change any shape encoded in those bases into the equivalent shape, bent, warped, done whatever we want to, that we did to the bases, right? So what does that look like in code, right? Well, this operation we know how to do in code, right? What's the operation in code of starting somewhere, moving along one axis, and moving along another, right? Well, it's really trivial. We just take the origin, right? Whatever the origin is, and I'll just, maybe I should write that with something else. I don't know. Well, I'll just write it origin. We start at the origin, right? If we're trying to get to a new point, right? So let's say we have one of these points here. In fact, I'll use, since we were using letters before, if I want the new A prime, right? I just start at the origin, right? I take AX and I move along that x-axis. I take AY and I move along the y-axis, right? And I'm at my location, right? So I have two coordinates, AX, AY, that encode the point. And all I need to know is, where is the origin? Where is the x and y? What are the directions that x and y point in? And how long they are, because this is baked in, right? This has a length, it's a vector, right? And I can produce the new point. Very, very simple, right? And so what we find is just with this, very simple equation, right? Which is like the offset plus the coordinate times the x-axis, the coordinate times the y-axis, we can do any kind of transform that we want that looks like, a rotation and a scale of some kind. And the scale doesn't have to be uniform, it can be non-uniform, right? That, in its most basic form, is a way to transform points. It's a way to do any kind of rotation and scaling that we want to do on points. So if we just wanted to move points around, this is all we really need to know, right? And this is where defining those bases comes in. So you can imagine if we wanted to define a basis, right, explicitly in code, it's something that just looks like, an origin, right? An x-axis, and a y-axis. Now again, what are these defined in terms of? It doesn't matter, right? The basis is just something that describes a space in terms of another space. So depending on how you decided to use it in the code, it's whatever this definition happens to be. If I took world space and wanted to define some little like I don't know, like a house, I wanted some house space, define like the space that was, a house that was rotated and scaled in the world somewhere, right? Well, I would just define this basis to be the origin of this house space in the world, so in world coordinates. The x-axis would be whatever the house's x-axis was defined in the world, and the y-axis would be whatever the y-axis was defined in the world, right? So if the world space looked like this, and the house is this tiny thing out here or whatever, then that's what I would encode. I'd encode that as the origin, I'd encode those as the x and y axes, right? And I'd be done. And then any point that was defined in this house space will automatically be at the correct placement, rotation, and scaling that I want it to be just by performing this transform on it, right? And so we've already done a little bit of this, right? We've definitely done the displacement. All we haven't really done is the scaling and rotating of those things. So we've already been doing this part, right? We've already been offsetting things all the time. The only thing we didn't do was actually start taking into account the axes, which would have allowed us to do that rotation and scaling, right? So this is what we'd like to introduce into our renderer now. Even though we don't really have much of a way to draw it yet, what we can do, for example, is we could draw some points that would basically give us the origin. We could draw like a little tripod, right? Because we have the ability to draw a rectangle. We could do something where we drew like this sort of a thing, the x point, the y point, and the origin point. We could sort of draw that, right? Those things, so we could see that we were computing it correctly. How do we actually define those, right? How do we actually define the x and the y-axis? Origin's easy, it's just a point. We all know how to move points around. We've done that a bunch, right? But how do we define these two? Well, here we come back to our unit circle, right? And that's a really easy way for us to be able to do that. If we have our unit circle and we sort of draw in the world, wow, that was a really bad circle. Let me try to do a slightly better circle. I don't know if I can. Drawing a circle on one of these is a little tricky. I'm going to be honest with you. Okay, forget it. The circle, oh my God, it's awful. Oh, it's just the worst. Oh, it's like lumpy. All right. Well, anyway, point being, pretend this is the unit circle. And when I say unit circle, I just mean a circle whose radius is 1, right? 1 unit. So, all right. If I have a unit circle and I want to take the cosine, right, and the sine of that, right? 2 values, cosine and sine. As my angle changes, right? So the angle kind of sweeps around like this, right? As the angle changes, essentially what I will get is the cosine value is the x-coordinate of the point that I would trace on the circle if I went out 1 unit along that angle, whatever that angle is. The cosine is the x-coordinate and the sine is the y-coordinate, right? So basically this here is cosine theta and this here is sine theta, right? Does that make some sense? Hopefully you've all had this in your grade school geometry class, or trigonometry class, sorry. Right? Makes some sense. So what that would mean is, well, if I was to plug in 0 for the angle, right? So if my angle was to equal 0, well, that would just be this point right here. And what is that point if this length is 1, right? That means the cosine theta was 1, the sine theta is 0, right? So at theta equals 0, that would give me a point of 1, 0, right? That gives me the x-axis. That's what that is, right? 1, 0. Similarly, if I was to plug in, 90 up here, 90 degrees, well, my cosine has now become 0, right? So if my theta is 90 degrees, then my cosine is now 0. And my sine is 1, right? And hey, guess what? That's the y-axis. So if, just without knowing anything else, if we wanted to create a rotated coordinate system, right? You can imagine using this just directly. My x-axis is just cosine theta, sine theta, because if it was 0, it'll give me the x-axis, and if it's anything above 0, it'll just slowly rotate up the circle, just like what I want, right? It'll just keep rotating, rotating, rotating around, right? And to produce the y-axis, all I would have to do is add 90 to it, because 90 degrees off the x-axis is going to be the y-axis, and that's just going to slowly rotate around this way too, right? So, cosine of this plus 90, sine of theta plus 90, right? That's the y-axis. So pretty trivial to generate rotated things. All you have to do is just use cosine and sine to pluck them off the unit circle for you. Furthermore, if I want to scale either of these, all I have to do is just multiply it by some number. That's my scale, right? Whatever I want my scale to be after these come out, I can just multiply by scale on the outside, right? Scale times either of these. If I multiply them both by the same scale, I get uniform scaling. If I multiply one by one scale and one by the other, I get non-uniform scaling, like I squash it, right, or whatever. So really, really trivial. Now, we can take this a step further and realize that actually, because we're in 2D, our situation for y-axes is really pretty basic, right? Because if you look at what actually happens here, let's say we've got that theta. Well, check out what happens when I draw on my right angle here, right? Oops, let's That's no good, right? So what I was saying is, well, you know, really, if you wanted to get this, you'd just do theta plus 90, and hey, there's that theta plus 90, so that gives you that point, and that's what I was saying down here. That's all good, right? But if you take a look at what this vector actually is, this is really just the same vector that we just produced, only starting with the y-axis instead of the x-axis, right? Imagine taking this whole diagram and just rotating the diagram 90 degrees this way, right? This is theta right here. It's the same angle, right? So it seems kind of stupid to recompute exactly the same vector effectively just to get it rotated 90 degrees. And so what you can see by, you know, looking at that kind of triangle relation, right? You can kind of see there, like take a look at how this looks, right? This here, these are the same. So this, right, is that right there. If you look at what happens here, you can even just reading off the diagram realize what a smarter algorithm is for producing that coordinate system, right? If this length is going to be the same as this length, because they're the exact same triangle, right? And this length is going to be the same as this length, then we already know the lengths of these two because we've already computed them up here, right? We've already done it. We know that sine theta, right, is going to be this length up here, right? Sine theta, sine theta. I should use the standard notation and actually double notch those, right? So if this is sine theta and this is sine theta, then really all I'm talking about is using the x, you know, which coordinate it goes into. It was going into the y coordinate here, it's going to the x coordinate now, right? Because of that 90 degree rotation, right? So basically, sine theta is my x coordinate for the y-axis, right? And then the same thing happens for the x-axis becomes the y-axis over here, right? This was the x-axis before. It's now on the y-axis, right? So what I want to do is take that cosine and I want to put it in here, right? And so you can see, essentially, to create the y-axis, all we have to do is rearrange, just flip which two we're doing. There's one more little rub to it, though, right? They're going potentially the wrong direction, right? Because cosine theta was positive going out this way, right? And it's positive going up here. So the cosine theta term will give us the correct answer for the length of this, right? As we come, you know, we want it to be positive, it's positive here, that's all good, right? So this looks correct, right? That looks good. But sine theta was positive here, it's not positive here, right? Do you see where this point is? This point is negative x, right? That's positive x in that direction, this is negative x. So we have to negate that one to put this point in the right place as it goes around, right? So we end up with the y-axis is actually just the same computation as the x-axis. We can just flip the terms and negate one of them. That's it, right? Really simple. Now here's the thing. You can also directly plug and chug this. I never remember them. I always have to look them up. But if you plug in your trig identities, if you remember these from grade school, your trig identities should tell you that cosine of theta plus 90 is negative sine, and that sine theta plus 90 is cosine theta, right? Those are actually trig identities you probably would have learned, and if you happen to remember them, you wouldn't have even had to look at the diagram. You could just say, oh, algebraically, I could just substitute in. I know that becomes this, and I know that becomes this, right? So that's another way to attack it. Last piece of interest here. Because we're in 2D, I want to talk about one more thing. So there's the concept of the perp operator, right? And no, that does not mean perpetrator. The perpendicular operator is the operator which takes a 2D vector and produces a vector that's perpendicular to it, right? What we have essentially done here is done the perp operator to the x-axis. Because the perp operator is just an operator that says, okay, if I have some xy, right, I am just going to output the y coordinate negated and the x coordinate the same, but flipped order, right? The exact same thing we did here, right? Swap the components, negate the x, right? And what this does is this actually creates the perpendicular for any vector in the space. Because no matter what vector I draw, right, I can always say, oh, I know that it has a y, I know that it has an x. Let me just interpret its x let me just interpret, sorry. Why am I got so far today without doing it. Remember yesterday I was drawing my x's and y's in different places all the time? I just did it again. It has an x and a y. There we go. I can interpret its y coordinate in the negative x direction, right? And I can interpret its x coordinate in the y direction, right? This way, and produce a 90-degree angled vector that's the same length as the previous vector, right? The lengths are the same, but that's pointing in exactly the perpendicular direction. And this is very handy, right? That allows us to quickly generate perpendicular vectors to any vector that we have in the plane, and it just works, right? It's super nice. And so that's what we actually did there, but you could see how we kind of constructed it, and you can also see how it works with the sines and cosines. So that means that essentially all we have to do when we want to create a rotated basis, right? If we want to create a rotated basis of theta, right? It is very straightforward. All we have to do is our x-axis becomes cosine theta, sine theta, and our y-axis is just the perp of the x-axis, right? That's it. We already know this is length 1 because, well, cosine squared theta plus sine squared theta, right? Square rooted equals 1. So we know that that's true. That's sort of a separate thing. So we don't have to worry about their lengths. We know their lengths will already be 1. And that is a trivial way to produce a rotated basis. If we want to scale that basis, we just multiply our axes by whatever we wanted to multiply them by, right? All good. All right. Let's see where we're at. 5:45. So we got time to actually just do this now that we've sort of basically done the lesson. No, don't open that. It's the wrong thing. The wrong command prompt. All right, there we go. So let's go into the code. Let's suppose that we want to create one of these little rotating doodads here, right? And we want to see it work properly. All we have to do, let's introduce just a totally synthetic render function that literally will have no use in our game, but just something, maybe we'll call it a tripod. I don't know. It's not really a tripod because it only has 2. So let's see, axis marker. I don't know. Coordinate system or something. I don't know. I'm not sure what to call it. I have no idea. But let's do exactly what we just said. We're going to have an origin, we're going to have an x-axis, and we're going to have a y-axis, right? And we just want to draw them. Okay, that's all we want to do. We just want to draw them. So if I wanted to do that, right, I need to just add a little thing here to, add in coordinate system, like so. And then I can add something to my render group that will allow me to push one of those onto my my render stack, right? So here we go. I'm going to push one of these coordinate systems, render entry coordinate system, and assuming that it came back okay, like so, I can assign its origin to something, right? Its x-axis to something, its y-axis to something, y-axis, x-axis, oops, that's no good, x-axis, and v3, x-axis. You know what? Might as well stick a color in there. Why not, right? That way we can have a couple of different ones on the screen and know which one we're looking at. There we go. So origin, x-axis, y-axis. Okay, should work fine. Now hopefully if we run this, well actually I guess we've got to make one first. We should get an assertion because we haven't put in anything to handle drawing it. But let's go ahead and actually put one in there first. I'm gonna, in our game state structure, right, I'm gonna add, just for the time being, a little thing that we can play with, which is sort of our, our angle or whatever. And maybe I'll put in our scale as well. You know what I could do? I could just do time. Let's do that for fun and profit. All right. So in here down at the very end, before we render everything, I'm going to say that our game state time is going to be equal to our, it's going to increment by our dt for frame, right? So we can do stuff with that. For now, I won't actually do anything with it. I'll just say that we've got an origin. Oh, you know what I just forgot to? I don't know why I forgot this. We're not actually in 3D right now. We're in 2D. There we go. So not going to be able to draw three-dimensional stuff yet. That's a bit of a problem. All right. So yes, if I have my origin, right? I have my x-axis. Man, I am just hung up on 3 dimensions today. And there we go. And y-axis, v2. Okay. And so if I now do that coordinate system call, and I push my origin, x-axis, y-axis, and whatever the color happens to be, let's go ahead and make a nice yellow there. That should set us up for success. Now it should, again, hopefully our renderer will stop on this and say, hey, wait a minute, I don't know how to draw that. That's the hope. And since we've never tested that, let's actually verify that that's true. One would hope. What is happening? What has happened, people? Why is our code hosed? What have we done? We are in the middle of rendering groups of what is happening? I have no idea what's happening right now. I'm going to step in and find out. We've totally broken it, so that's good. You know, sometimes you have to break everything. What did I do odd there? There's the clear. We should get to one we don't know, and then we should hit our invalid default case now. But apparently not. I guess our invalid default case is not working, which is a bit odd, to say the least. Let me see what our invalid default case says. Handmade.h. All right, it's probably in platform, huh? Invalid default case. Valid code path. That kind of looks right. Although that should not have a semicolon after it, but that's not really an issue. Yeah, that should stop us. Well, I can't say I know why that's happening. But what I would like to do to debug that is let it hit that guy sooner. Let's put the coordinate system so that it happens immediately upon startup. That way, we will see what happens when we immediately step into it, if that makes sense, so I don't have to kind of loop through everything else. So it should. Why does it not hit? Is clear? So clear should not have been the first thing in the render state. Am I right? Like, we should have had a thing where it was pushing the coordinate system. So I'm going to go ahead and take a look at that buffer and see why that's not happening. Let's go into Handmade render group. Just make sure, because we're pushing render entry coordinate system, right? So the type of that should not be clear. It should be coordinate system. So the first thing on our stack should be one of these coordinate systems. So let's see why it's not. All right, come in here. Let's take a look at our render group. Render group. The render group's got the push buffer base address, right? And the first thing in it is a 0. That doesn't make any sense to me. Oh, because we're in fill ground chunk. All right. Forgot about that. So yeah, I guess we have to actually run to here. Let's try that one more time. All right. Now I can see what it is. So how is our push buffer base still showing that the first thing in it is a clear? Someone explain that to me. Somebody explain that to me. All right, well, I guess we'll just have to see where our push isn't working. Probably a bug that I made. So here we go. We'll make the render group. There we go. And look at the push buffer base. Step into coordinate system. Right. This is going to make a... Oh, hello. Don't actually need to quite step into that, but thank you. All right. Why is this not... Why am I not able to step into this? Coordinate system. All right. So it thinks it pushed a render element on there, right? It certainly appears to believe that it did that. And the push buffer base has actually done exactly what it should have done, which is set it to 3. It sets the... Yeah, there we go. Asleep at the switch. Oh, it's been a long day, people. It has been a long day. I forgot to put my little header in here. There we go. So that's the problem. Yeah, all of these guys have to have a header for now because we don't really have anything in particular. I should probably get rid of that because that's not actually necessary. And it's just prone to error, as you just saw me make, when you forget about what you're doing. Because really, we don't need this header value to be there. I'm just going to say go ahead and remove that, so I don't make that mistake again. Remove the header, because we don't actually need the header to be listed in these guys. That was just kind of a short-term thing that's just kind of sloppy. I don't want to remove it right now because I'd like to finish what we were doing. But suffice to say, yeah, totally not necessary, and I would prefer to not have that be a potential source of bugs. It's just there's no need for it, basically. Let's put it that way. So yeah, we'll fix that tomorrow, but because I'd rather not go through it right now. So let's go ahead and put our coordinate system back in there. So now hopefully we will get a thing that stops us and says that it doesn't recognize the thing that it was doing. Now why, of course, there we go. It's because we haven't put in a case for our coordinate system. So all we should have to do now is put in a case for our coordinate system. Yeah, and then we should see it show up. So in here, I'll say, all right, we've got render entry coordinate system, and all I want to do here is grab that coordinate system out, and I guess, you know, well, this is in pixels, right? So whatever that coordinate system is actually going to be in pixels. I don't know if we want to try translating it out. Yeah, let's I guess leave it. Let's do a little bit of translating it out. What do you think about that? Do you think that's okay? I'm thinking that maybe that we just do the screen center amount. Well, you know what? No. All right, we'll just do it in pixels so that we can see it directly, because that seems, I guess, like more in the spirit of things. All right. So if I do draw a rectangle, I basically need to draw some little rectangles so that we can see this stuff. And so entry color R, entry color G, entry color B, right? So there's my color values. I then need to have some kind of a dimension. Let's say that our dimension is going to be, you know, a 4x4 pixel square or whatever. Or I guess in this case it would be a 5x5 pixel square. And then I will create the p-value by taking the origin, right? And now we should, I think that actually should show up, although we need to actually define it to be something that will actually be visible in pixels. So the origin, let's put it right at the screen center for now. And we'll say that our x-axis is maybe like 100 pixels, even though we're not using those yet, right? So let's see if we should be able to see a little pixel for this. And there it is right there. You can kind of see it. It's underneath me. Although the color value seems wrong, which I'm not exactly sure why that is. Yeah. Draw a rectangle, color R, G, and B. I feel like that should have been right, but it looks like the color was wrong to me. Not the end of the world. We'll deal with that in a second. But all right, so if I was to take this and then draw the rest of those guys as well, like the x and the other two axes, right? All I need to do is create the other points the way that I said I was. Start at the origin and go out along the x-axis. So here we go, x-axis. In this particular case, I don't actually need a scale for it, so that's fine. And then similarly, if I go out along the y-axis, that'll be a point that's 1 unit along that axis as well. That should give me basically that sort of tripod of points that are 100 pixels apart. You can see them there. I just don't understand why their colors are that way. That's kind of bizarre, don't you think? Super weird. Yeah, very strange. So let me check out why the colors are what they are. The entry color RG and Bs getting passed there. I'm just gonna set a breakpoint in there and see what those colors are actually getting set to. Let's take a look. So what's our entry color? Our entry color is all zeros. All right, that doesn't seem good. Well, that would do it. Wow, 2 asleeps at the switches today. There we go. Okay, there's our little coordinate system, right? Pretty straightforward. So if we want to do exactly what I said on the blackboard now, it's really pretty trivial, right? I said what I wanted to do. Let's make the length of this be something that we pull out on the side. So there's our scaling, right, of the axes. Let's make this be a cosine sine, and we'll make this y-axis. We'll just make that be the exact perp, the perp that I said before, the perpendicular to the y-axis. Oops. Right now, I don't actually know if we ever put in sine and cosine. Did we? I don't think we did. No, we didn't. So we have some math to dos. Oh, well, you know what? We might have it in our inlines. Did we have it in our inlines? I don't know where. Like, where's our square root, for example? Right? We have intrinsics square root. Do we have a cosine? We do have a cosine. Okay. So if I do a sine and cosine of some angle, right? Then all I have to do is just say, well, okay, let me base that angle off of the time value that's going up there, and then we can sort of have, you know, a rotating basis vector, or at least we should have a rotating basis vector, right? And there you can see it rotating around exactly like we said it would on the blackboard. Now let me go ahead and sort of do this live so you can kind of see what happens as you play around with it, right? There's that rotation. So if I wanted to, right, I can change the size of this coordinate system, right, by changing whatever that scale value is there, right? You can kind of see I can make it much smaller, and then I get a smaller rotating one. I can also make it much larger than it was before, and then I'll get a much larger rotating axis system, right? And again, anything I encode in this axis system that gets pulled out using that formula that I was talking about before will still be encoded properly, right? And so that's really all there is to it. Yeah, I can also introduce non-uniform scaling by scaling up, you know, whatever the y-axis is. So now there's one. Oh, well, that's actually too large, isn't it? Well, I'll be off the screen. Now we have like you know, one that's more elongated, right? And you can imagine us taking any sort of points that are in here and having those be rotated and scaled as well. Again, just by taking them and interpreting them in that coordinate system. And so just to show kind of an example of what I mean by that, right? You can see, let's say that in the render group, right, we just had some points that were encoded in that axis, right? This is purely synthetic, just again, as a thing to show for educational purposes. Let's say there were some points, right? Let's say there were maybe, I don't know, let's say there's 16 points or something like that, right? And I'm going to go ahead and say that we'll just render those points using that formula that I said previously, right? So if I come in here to my render group, and inside here, I just render those points directly, right? So I say, all right, for, you know, p index equals 0, p index is less than that array count of whatever the entry points array has in it. I then say, all right, the entry points, whatever it is, That's the new p coordinates that I'm using there, right? So if I want to generate p here, I do exactly that formula that we wrote on the whiteboard. I do, I'm sorry, the blackboard. I do p.x times the x-axis plus p.y times the y-axis. So start at the origin, walk out the x-coordinate along the x-axis, walk out the y-coordinate along the y-axis, and that's my new point, right? And then I'll draw a rectangle there so that we can see it, right? Make sense? Pretty straightforward. So all I need to do is actually initialize some points in there, and what I'll do here is I'll just do a really simple grid for us to use there. So let's say I take you know, an x of 0, I'll do x is less than 1.0, and I'll do x plus equals 0.25, right? I guess I should say less than or equal to, and I'll do one here as well, so we can have a y as well. And then I'll just say, you know, all right, we've got p index equals 0, and we'll say that our coordinate system, I will need to actually be able to get one of these. What is it? Render entity coordinate system. There it is. Render coordinate system. We'll just grab that out. And we'll say, okay, points p index plus plus equals v2 xy, right? So now we're literally just making a grid. Like we're making the x's go along quarters and the y's go along quarters, right? Now I introduced the notion here that I would return that coordinate system, so I gotta kind of actually do that, right? So that it can get filled out by the calling code, return entry, like so. And if I do that, now I should get that little grid, right? Or not. I should get that little grid. Apparently I don't get that little grid. V2 points, am I actually properly initializing that? Yes, p index plus plus, y equals 0, y less than, that's, yeah. Just trying to race the clock here. I got only about 5 minutes left before I got to stop. So sorry for the abbreviatedness of it all. That looks correct. So then where's my rendering? P index wake count points, v2 is p, or p.x times entry x-axis p.y. That should have done it. Why did that not do it? Let's take a look. So let's go in. Oh, wow. It'd be nice if I actually used the index. There we go. So get rid of that. That is not what I would have expected at all, to say the least. What did I must have initialized my points slightly wrong as well. Hold on one second. Where is, there we go. We're almost there. Just got to debug a few more things. My x and my y. Let me take a breakpoint there. This was kind of a sloppy way to do this. I had to do it kind of quickly. So let's see. 2, 5, 5, 7, 5, 1. Right? Initializing all the points properly. There we go. Oh, but that's too many. That's the problem, right? That's one too many. Yeah, my bad. That's more than what would fit, right? Because you can't actually, yeah, so I'll have to do it basically just in the first portion. There we go. I'm only allowed 16 points. I don't know why, but that's the amount I did. So there, now we can actually see sort of a more accurate version of sort of what the space looks like, right? And you can kind of see essentially whatever I do, and you know what, I'm gonna turn off the recomputation of ground buffers as well. So you know, we had this executable reloaded thing. We don't actually need to do that for what we're doing now. So I'm gonna leave this running, and I'm just gonna go ahead and play around with those axes. So remember, the only thing that we're doing in here is we're just interpreting those points based on the coordinate system. We're starting at the origin, we're walking out along the x-axis by whatever the x-coordinate is, and we're walking out along the y-axis by whatever the y-coordinate is, right? So now I'm just gonna change the two axes. That's all I'm gonna do. And I'm not going to touch what the point definition is. The point definition is going to stay the same, right? So let's say that I was to reshrink the y-axis so that it's like the same scale as the x-axis, right? You can see that now I get back to a square, right? Or I could sort of blow it out significantly more, and you see that it stretches out more, right? Another thing that I could do is I could, and also you'll notice that they're always rotating around properly, right? Another thing that I could do is just get totally wild with it and say, you know what, I'm not going to make these be perpendicular. Instead, I'm actually going to make these be skew, right? So I'm going to take the angle and I'm going to add, you know, some amount. Do we have pi yet? I don't know if we have pi. Let's find out here. I don't think we've ever covered this on Handmade Hero. Do we have pi? Yes, we do have a pi. I guess? I'm not sure. I'm not sure if we have pi or not. Well, I'll just say 1.5f. How's that? Is that better? Hopefully that's better. Why am I collapsing? Why is that producing the same value? Is that odd to you? Oh, because it's 100. There we go. All right. So if I was to make this be just some offset angle, so I'm producing another angle and I just make it be something that's not 90 degrees anymore, right? You can see that I can actually skew all of the points that are defined in that system as well, right? I can be as ridiculous as I want to be. And by morphing those axes, right, I'm going to morph all the points that are inside them. And similarly, I can make something that's, you know, sort of smushed up in addition to, right? And so that's really all there is to understanding the rotation and the scaling transforms. It's just taking those axes and bending them, then all the points, because you're constructing the points by moving along those axes, there you go. Similarly, the origin is the same. You know, if I introduce some amount of wiggle to that, right, all the points, obviously, we know they will get displaced in much that same way, right? So I can adjust their position as well. So with origin x, y-axis, it allows me to have a tremendous amount of flexibility with how I'm placing my points. We haven't actually talked about how we're going to render stuff yet in that space, but at least we now know kind of, or can see very simply, how those bases come together, right? So I'm going to leave it there because I'm just about out of time here. So I'm going to go ahead and say, let's go to the Q&A so we can cover any questions that we might have. And then tomorrow we can sort of clean this stuff up. And you know, I'll put a to-do in here. To-do, Casey, let's add a perp operator, right? And off we go. Any questions? Any questions? Kind of a weird thing here. Sorry I had to slam in these weird points. This is completely ridiculous right here, but I just needed something quickly so we could show how things were interpreted in that space. So if you have questions, please prefix them with Q:, so I can read them. But yeah, chat is a long time behind the video. Really? Okay. I don't know why that is. Was there some kind of a drop frames? No, I guess it's just Twitch. Twitch was a little laggy. If there are no questions, then, you know, we'll be done early. Well, of course I took 10 minutes of extra time, but because I started like 10 minutes late. Do you usually worry a lot about naming schemes? You always seem to choose a good enough name and move on. No, I don't worry about naming schemes hardly at all. As long as something seems reasonable enough, I think that's fine. You can always change it later, so it's no big deal, right? John, I don't know how many times I have to tell you this, but that can't possibly be the variable. How could it be the variable? No one has ever seen a variable. I mean, like, it's not even remotely plausible that that could be the variable. It's just a spinning little diamond thing. How can you draw so fast? You use the draw pad and pen. Yeah, I have like a little Wacom graphite, like the little, or Graphire or whatever it is. Garlando Bloom, I only partly followed, but it seemed fairly easy to get the basic rotation up and running. I'm wondering how much more work it will be to start rendering textures by sampling them across the plane. It's not much work. We can do it pretty well. So also, John, I feel like if the variable did exist, it probably exists in between the points that are rotating here somewhere. Like the variable could be in there and we just can't see it. You know what I mean? Because it's invisible. I do filter on Q colons when there are enough questions, but there aren't that many, so I flip back to the chat and just see what's going on when there aren't a lot of questions, when there aren't a lot of Q colon questions. Next up, is it possible to do realloc with Memory Arena? It depends what you mean by that, right? So I guess what I would say is realloc by definition is allowed to return you a different memory block. So technically you could easily implement that with Memory Arena by just allocating a new space at the end of the arena and returning that as the pointer, right? But if you're talking about realloc as in allowing memory to grow, then no, because the arena is always tightly packed. That's kind of the point of it. So in that sense, you'd never grow a memory block in the arena unless it was the one at the end, right? Are parametrics and polar functions going to be used later on? Well, you know, origin systems like this are basically like, I mean, that's sort of what they are. They're like uber versions of polar functions, right? So you basically define stuff and then you can rotate it however you want. Polar functions themselves are not typically that useful unless you're trying to construct a basis, because usually you're trying to do, like, we constructed our bases with polar coordinates, right? I mean, that's polar coordinates right there, folks, right? So, you know, you don't usually think in terms of polar coordinates in that sense, though. Parametrics, I mean, again, everything we've done so far has been parametric, right? So yeah, I guess it depends if you're talking about something specific. Will subpixel positioning and anti-aliasing be part of the software render in the exploration phase? Actually, we're not really doing the exploration phase for the render right now. We're actually just doing the renderer, so we're going to do anti-aliasing and positioning. And we'll just do it, so it'll be done. See here. Looks like there's no more questions, probably. I'm not seeing any more questions on programming, or on the programming we're doing, I should say. This could be part of the lag, as you were saying, though. Maybe people are just about to ask a bunch of questions and I just can't see them. This thing's kind of funny, sitting there like that. I feel like we should make the size of it proportional as well. So it's like, you know, oh, it's like 100, but it's plus 25.0 times, you know, cosine angle, 1.1f times angle or something, right? So that, you know, it kind of shrinks and grows. like so, right? I mean, that's really the way you want it to go, right? I do like it. I like the description of it, Christmas tree Triforce. That's pretty funny. People think that's trippy. You can keep going, right? I mean, you can just go nuts with that if you want to. Right? I think we ran out of questions too. But we have, yeah, like basically vector bobs is what we're doing right here. Time-dependent color. Oh, man. All right. Well, you know, if you want it, you got it. I'm here for your amusement, right? Off we go. Better? I mean, basically, like when we add particle systems, if you guys think this is fun, like particle systems, I guess people are going to go nuts because that's what particle systems are. It's all this ridiculousness, right? So yeah. Yeah, and Handmade 4K demo, I'm not qualified to do. I just don't know the 4K tricks. Fabian could help out with that. That's where Fabian comes in. He should show us how to do a 4K demo. So needs more dots. All right. We're not gonna. Yeah. Let's not. This was meant for demonstration purposes. We're not gonna rat hole on that. When we get to particle systems, we can rat hole on particle systems for a little while, but that's probably not the best thing to be doing at the moment. So let's leave that be for now. All right. I am going to. Oh, that's the variable. It has now quit the variable. All right. Let's call it done for the day. I think that's good enough. I think that's roughly where we want to be for that. It's just kind of ridiculous. Why is that happening? All right. Well, anyway, if you do want to watch it forever, Garlando Bloom, I will upload the source code as it is right now so that you can download it and just leave it playing on your machine forever. And there you go. All right, I will wrap it up here. Thank you, everyone, for joining me for another ridiculous episode of Handmade Hero. That little weird pulse setting thing was pretty freaky. I hope you've enjoyed it. I know I have. If you would like to follow along at home with the source code and make your own modifications to the little flashing weird dot thingy, you can go to handmadehero.org and pre-order the game. It comes with the source code so that you can play around with it yourself. You can also go to our forums and ask questions or use the resources there. There's ports to Linux and Mac if you want to follow along on other platforms, or if you want to use the annotated episode guide to catch up with stuff. We also have a Patreon. If you want to support the video series, you can subscribe there. And there's a tweet bot that tweets the schedule. If you want to know when we're going to be live, that's the place to go. So I hope to see you guys all tomorrow, same time, same place, 5 p.m. Pacific Daylight Time here on Twitch. When we will actually start implementing, I guess we might just go for it and start implementing rotated and scaled textures, just so we can kind of see how that's starting to work. But there's probably a lot of Blackboard work we got to do, so we probably won't. That'll probably take a couple days, so we'll see how it goes. But anyway, hopefully you will come back tomorrow and join me for that. I'd love to see it. If not, have a fabulous Thursday all the same. I assume it's Thursday. Is it Tuesday? What day is today? It's Wednesday. Have a fabulous Thursday all the same. And I'll see you on the internets. Take it easy, everyone.